Hi there, and welcome to this series of videos to help you with your maths revision. So giving you time to look at a question, decide how you would start it, and then going through the answers. A daily dose of 3 questions, 1 pure, 1 stats, and 1 mechanics. So let's get started. Each video will show you a question, give you some tips by focusing on the keywords and drawing out how to approach that question, and then giving the answers. So here's today's pure question. So have you spotted reading this question? We've got this n term, which is 4x to the minus 1, which is the same as 4 over x. So it's not quite your normal quadratic because of that term there. We've got the k in front of the x and we're being asked to find k, but we're given that the curve has a minimum when x is minus 2. So when you have a minimum, that's a turning point, and the gradient at that minimum point is going to be 0. So we need to differentiate and just treat the k as a constant, and then sub in that x is equal to minus 2 and equate the gradient to 0, and then that will find us the k. And then reading the next point, we've got a point of inflection, so we need to determine the nature of the stationary points, and how you do that is you take the second derivative, and when you have a point of inflection, the second derivative is 0. So we're told that this curve has a minimum point when x is minus 2. So at a minimum point, the gradient function is 0. So this graph, if we drew it at x equals minus 2, there's going to be some sort of local minimum. So before that turning point, the gradient will be negative, then it will be 0, and then it will be positive. So what we need to do is differentiate. When you differentiate, you power down and take one off. So dy by dx is going to be 2x. The kx term just goes to k, and then when you power down, the minus 1 times the minus in front of the 4 there is going to give you a plus 4, and we take one off the power. 1 down from minus 1 is going to give us that minus 2. Well, now we know that that is equal to 0 when x is minus 2. So what we need to do is substitute in to dy by dx that x is minus 2, and when we do that, we get 2 times minus 2, which is minus 4, plus the k, and then this term here, 4x to the minus 2, means 4 over x squared. The minus 2 on the x means that that's underneath, and when we put minus 2 in there, you're going to get 4 over minus 2 squared, which is 4. So that's going to give you that term there, which is actually 1. And then take everything to the other side and solve, and you get that k is equal to 3. So I've rewritten the curve here with k now equal to 3. Now in the next part, we're asked to show that the curve has a point of inflection which is not a stationary point. Stationary points are where dy by dx is equal to 0. Now, a point of inflection is when the second derivative is equal to 0. So we've got our first derivative here, and we just need to differentiate again. So the 2x term is just going to go to 2. The k, which is now a constant 3, that will just go out, and then the last term will power down again. So the minus 2 times the 4 will give us minus 8, and taking 1 off will give us minus 3. Now equating that to 0, taking the minus 8x to the minus 3 to the other side, and the minus 3 just means that that x cubed is underneath, and then we can cross multiply and get that x cubed is equal to 8 over 2, which is 4, and then to get x, it's going to be taking the cube root, so x is going to equal the cube root of 4. Now when x equals the cube root of 4, if I put that back into the first derivative to prove that this is not a stationary point at that point x equals the cube root of 4, when we put it back into dy by dx, it is not equal to 0. So we have got a turning point at the cube root of 4, but it is not a stationary point because the gradient is not 0. So what's going to happen, we've got a point of inflection. So you can have two different types. A point of inflection is where the curve slows down and carries on with the same gradient. So it can either slow down and actually go flat in the middle, so the gradient would be 0, or it can just slow down and then carry on. So you can have it coming down negatively, or you can have point of inflections going up. So things to look out for here, we've got a stem and leaf diagram. So obviously the stems are going to be down the left, the marks, and the leaves are the to the right of that line. And looking at the key to the line 6 means we've got 26. So 1 and the 4 means we've got 14. The totals here are just how many values are in each row. So have we got an ordered stem and leaf? All the leaves are in order, so that's going to be helpful when we're going to calculate the quartiles. So we're told here to calculate an outlier, which is going to be 1.5 times the interquartile range above the upper quartile and that same distance below the lower quartile. So we need to find the upper and lower quartile and then do that calculation and then see whether we've got any outliers. So we're being asked to list whether we have any outliers, and we're using the calculation in this question of 1.5 times the interquartile range above the upper quartile and that same distance but below the lower quartile. So we need to find the upper and lower quartile. Now we've got 31 values by adding up all those totals. If we do 31 divided by 4, and because that comes out to be a decimal, you always round up. So the 8th value along is where the Q1 is, and if we count along all the values, we've got 1, 2, 3, 4, 5, 6, 7, 8. So 46 is going to be Q1, the lower quartile. Now if we find 3/4 of 31 to find where the upper quartile is, 3/4 of 31 gives us 23.25. Now again, you always round up, so we want the 24th value is where the upper quartile is going to be. So if we count backwards from 31, 31, 30, 29, 28, 27, 26, 25. The 24th value is going to be a 63. So the interquartile range is Q3, the upper quartile, minus Q1. So that gives us 17. So if we look at the lower quartile, which is 46, and we take off 1.5 times that interquartile range, that comes to be 20.5. So we can see any values that are less than that cutoff point are going to be outliers, and we can see we've got one which is a 14, so 14 is an outlier. And then if we take the upper quartile and we go 1.5 times the interquartile range above the upper quartile, that will get us to 88.5. And so we can see at the upper end we've got another outlier, so that is going to be 90. So what you're looking for on your box plot is the interquartile range. You do 1.5 times above the upper quartile and 1.5 times below, and anything beyond there, those points are going to be outliers. So in this question, it represents a train travelling between two stations, and the two stations are 1.5 kilometres apart. Now remember that the distance is represented by the area under the graph. So the area of that entire trapezium is 1.5 kilometres. But we also notice that the units for everything else is in metres. We've got metres per second on the y-axis for the velocity. So if we change that 1.5 kilometres, the area of that trapezium is going to be 1500 metres. Now we're travelling and accelerating uniformly for the first section until we reach that constant speed. Then the train is travelling at a constant speed before it decelerates back down to the next station. So we're told that it's accelerating uniformly for the first 300 metres until it reaches that speed. So that is the area of this triangle here is going to be 300. So we can use the formula for the area of a triangle, half base times height, to find the time taken to get to that constant speed. We're then told that we are decelerating at 1.25, so the gradient of this last section is going to be 1.25, and we can work out the time taken to decelerate down to the station. And then the formula for the area of a trapezium is half into a plus b h, and we can use that to equate it to 1500 to then find the t that we're being asked. So the train is travelling between the two stations, and the first 300 metres represents this section here, because the train is accelerating from rest to reach that constant speed. So the area of a triangle is half base times height, and if we just call this distance here t1, then we've got half times t1 times 30 is equal to 300. Half of 30 is 15. So t1 is 300 divided by 15, which is 20. So the time to take until we get to that constant speed is going to be 20. Then using the fact that the gradient of the deceleration is 1.25, gradient is equal to rise over run, or change in y over change in x. So 30 over t2, calling that section of the journey t2 is 1.25, just cross multiply and get that t2 is 24. So the whole of that section there took 24 seconds. Now the area under the whole curve is a trapezium, so the area of a trapezium is this formula here, so half a plus b h, where a and b are the parallel sides and h is the distance between them. So just filling everything in now, we've got a, which is going to be all this section here, which is made up of a 20, a t and a 24, and then b is this section here, and that is just t. So we've got half a plus b and times the distance between them, which is our 30. So just half of 30 is 15. Cross multiply and take that to be a divide on the other side. Collecting all this in the middle comes to 2t plus 44 is equal to 100, and then take off the 44. 2t is equal to 56, so t is equal to 28 seconds. Thank you so much for watching. Hopefully this has helped you with your revision. If you have any comments that you want to leave, or any particular questions you want me to focus on in any of the three strands, the pure, the stats or the mechanics, please do leave any questions. Please do like and subscribe, share it with your friends, do all that good stuff. I would really appreciate it, and I will see you on the next one.